Okay, so we'll start looking at the, just going through briefly the fundamental stuff on geometry and focus on some of the important things. So some of this you would have seen already. So basic stuff like lines and angles. You need to know what a line is, a line segment, a ray, those things you can go through. The difference between degrees and radians, conversions from radians to degrees, or vice versa. The different types of angles. So what an acute angle is, right angle, obtuse, or reflex angle. Right, and then things like vertically opposite angles. So if you have two parallel lines, so basically, right, this thing. So if you consider the angles A and B, those are adjacent angles, and adjacent angles add up to 180. A and C are vertically opposite, they're equal, similarly to X and Y. A and X are corresponding, similarly Y and C are corresponding angles, so they're equal. And A and Y are alternate angles, they are equal. Similarly, B and Z are alternate angles. A and Z are interior angles, they add up to 180. Similarly, B and Y are interior angles, they add up to 180. Right, now if you have two lines, right, this is assuming the lines are parallel. If you have two lines and a line cut in those two lines, and if you can show that, for example, this angle down, this angle here is equal to this angle up here, then that basically implies that the lines are parallel, right? Because that's the only way it's going to hold. So the converse of all of these things are all true. Two definitions you need to know for, well, when things are collinear and when things are concurrent. So collinear refers to a line on the same line. So points are collinear if they lie on the same straight line, and lines are concurrent if they intersect at the same point. And we'll talk about this more just now. Now, there are actually two theorems that you can use to prove things being collinear and concurrent. Those are called Sever's theorem and Menelau's theorem. That's not covered here, so, but hopefully you'll see it at some point. Right, tips for approaching geometry problems. This, again, we've gone through this already, so I'll leave this up to you to read. But important things: draw a big, neat diagram, use your compass as much as possible, and label your diagram properly. Every time you introduce points, you state what they are. Right, and try not to draw the diagram too equilateral or isosceles unless you're specifically told that it is equilateral or isosceles. Right, those are the things you can go through. Okay, so triangles, different types of triangles. The triangle, well, a triangle can be scalene if the different sides and different angles are not equal. Isosceles if two angles are equal, equilateral if all three are equal, right angle if there's a 90-degree angle, and acute angle if all angles are less than 90 degrees. All right, okay, this is the important part. So this is talking about the different types of lines in a triangle. Now, before we actually go into this, you do need to understand some stuff about similarity and congruency. So for the time being, I'm going to skip this and we'll come back to it just until we finish this next section, couple sections. So similarity. Right, I hope you know what similar triangles are by now, but just in case, two triangles are said to be similar if you can show that the corresponding angles are equal, or if you can show that corresponding sides are in the same proportion or same ratio. So for example, if you have two triangles ABC and PQR, we say they are similar, we denote similarity with this symbol here, tilde, right? Well, these two triangles are similar if and only if the angle at A is equal to the angle at P, and the order I write them is important. If you write ABC is similar to PQR, then A, the angle at A has to be the angle at P, the angle at B must be the angle at Q, and similarly, the angle at C must be the angle at R. Right? And as well as that, if you take the ratio of AB divided by PQ, it's the same as AC divided by PR, which is the same as BC divided by QR. Right? So I always like to write them next to each other, or maybe one above the other. And then you go, well, if I take AB here, I have to divide by PQ. If I take BC, I have to divide by QR. Right? So you can kind of match them. Now there are other things you can do with this, but for the time being, we'll just focus on this part of it. So what I mean is, for example, let's take this one, right? This part of the equality. I could divide by BC and multiply by PQ, and I'll get AB divided by BC would be the same as PQ divided by QR. So the ratios don't have to be for one triangle divided by another. You can have the ratios for one of them together, and then it will be the same as the ratios for the other one. There are two ways you could look at the proportions for the sides in that aspect of it. Now, basically when two triangles are similar, it means, yes, they have the same angle, so they have the same shape, but not necessarily the same size. Right? That's important. They can't have the same size. If they have the same size, yes, they are still similar, but well, we call that congruent, which we'll talk about just now. All right. If you want to prove that two triangles are similar, the easiest way to do it, usually the easiest way, is to show that the angles are equal, corresponding angles. Now, here it's listed as AAA, meaning all three pairs of corresponding angles are equal. But technically, once you show two pairs, the third one must automatically be equal, because I mean, the third one is just 180 minus the sum of these two. Right? So for example, if the angle at A is equal to the angle at P and the angle at B is equal to the angle at Q, this will automatically follow, because the angle at C is 180 minus the angle at A minus the angle at B. And then similarly, this is 180 minus this angle minus this angle. And because of these equalities, it is automatically true. So even though it's stated AAA, you don't have to go and say, well, all three pairs of angles are equal. You just have to show two of them, right? And it follows from that. Now with the sides, you have to be careful, right? This one, the same thing up here, where I said you only show two, you can't do that down here. You have to show all three, right? So you have to show all three. You have to show this entire thing if you want to use this to say the triangles are similar. If you just say AB divided by PQ is BC divided by QR, that's not enough. You need this one as well. Right, and then the third one is SAS, side angle side. So what this means is that you showed two of them corresponding, two of the corresponding sides are in the same proportion, and then the included angle is equal, meaning the angle between them. If it was two adjacent sides and then an angle on the outside, or one of the other two angles, then that doesn't work, because you could draw two triangles, two different triangles satisfying those properties. Basically, one of them would be acute and one of them would be would have a obtuse angle. Basically, 180 plus the angle you had before, or 180 minus. Right, you could try to draw it and see yourself. If you take a point, right, and then you have two sides. I could try to show you the construction for that, but I didn't actually prepare it beforehand, so it might take some time. All right, let me briefly try to show you something here. I don't know how long this is going to take. You all see in the screen, right? Can somebody let me know if you all seeing this properly?
Yeah.
All right, so suppose we had two sides that were equal, but then the angle wasn't the included angle. So for example, let's say I know this line AB is of whatever length this is. Let me draw that segment. All right, so I know this is whatever length. And I know the length of AC, right? So I could say AC, I know the length of it, and it lies somewhere on this circle. C would lie somewhere on a circle because the length, let me put it up here. All right. If I know the length of AB, I can draw the line AB. And if I know the length of AC, I know it would be somewhere on the circle because it has to be at a fixed distance from A. Now, suppose I didn't know the angle BAC, right? I didn't know the included angle. Because if I knew the included angle, then I know exactly what the triangle is. But suppose I know the angle down here. Suppose I know the angle for B. So how do I do this now? All right, I haven't used this to construct angles, so it may not be easy to. But anyway, so let me draw a line, right? Suppose I know the angle here is whatever this angle is. Move this. Move this point out of the way because we don't care about what it is. Right? Suppose I know that this angle is, I don't know why this does that. Right? If this angle here is 142, it means that this angle here would be 37.6. So let's just say whatever reason I know the angle 37.6, so I draw that line. If you look at the intersection of that that angle with the circle, right, it'll give you 2 points. So basically it means that the triangle right, the triangle could actually be either this or it could be that. And both of those triangles satisfy the given conditions. All right, I'm gonna hide the point C. So C could either be at E or it could be at F. And regardless of where it is, I know the length of AB, I know the length of AC, whatever it is, those are fixed, and I know the angle. Right? But these are two completely different triangles. So it doesn't necessarily mean that the triangles are similar if you have SS and then A on the outside. The A has to be between the two of them. Right? So I need to know the angle. If I know AB and I know AC, I need to know the angle between the two of them in order for me to conclude that, to know what the triangle is or to conclude anything with similarity. All right, so that is all to do A. All right, this note down here just corresponds to what I just tried to explain. This is an important theorem, the midline theorem. It basically says if you have a triangle ABC and you have M and N at the midpoints of this triangle, of the sides of the triangle, if you connect those points, then basically this segment MN is parallel to the third side BC and is also half of the length of BC. Right, and the proof for this uses similar triangles. So I know M and N are the midpoints of AB and AC, right? So we know that AM is a half of AB, or in other words, AB is twice AM and AC is twice AN. So if I look at the ratio of AB divided by AC, right, that would be the same as AM divided by AN because the twos cancel. So AB divided by AC is AM divided by AN, and the included angle is the same in both because this angle doesn't change. Angle BAC is the same as angle MAN. And because of that, we have SAS similarity, right? Or we can use the SAS condition for similarity. It means that triangle BAC is similar to triangle MAN, right? And then once you know that those are similar, well, automatically angle AMN is equal to angle ABC, which implies parallel lines, right? Because these are corresponding angles. So the lines are parallel, and also because of the similarity, we know the ratio of AB to AM is 2, and AC to AN is 2. So automatically the ratio of BC to MN will also be 2. And that's how you get the ratio. Right? Now the converse of this theorem is also true. When I say the converse, I mean if you didn't know that M and N were the midpoints, right? If you know that, let's see, how do I say, what do, well, another way to say it is if you're given a triangle ABC and you know M is a midpoint of this side and N is a point on this side of the AC such that MN is a half of BC, then automatically this thing will be, N will be the midpoint of the side. Is that necessarily true? Okay, I'll have to think about that a little bit. But yeah, basically if M and N are midpoints, then this thing is true. Then MN is parallel to BC and MN is a half of BC. Now, if you weren't told, okay, what I was trying to explain is if you weren't told that M and N are midpoints, right? You're just given points M and N such that MN is parallel to BC and MN is a half of BC, then automatically M and N are the midpoints. So that is what I meant by the converse. Right, so if you're given this, then automatically M and N would be midpoints. All right, I'm not gonna go through this, so you all could look at this, or we could come back to it at the end if you want me to clarify anything. The next part of it is congruency. Congruency is basically where triangles are, yes, they're similar, they have the same shape, but they're also the exact same triangle, meaning they have the same sides. So this is more a stronger condition than similarity, and this is the symbol we use here. Right? Again, the order matters. If you want to prove triangles are congruent, then the sides must, you're not looking at ratios anymore, right? You only look at ratios for similarity. For it to be congruent, they must be exactly the same length. Right? I don't mean the sides of triangle ABC must be the same length. I mean AB must be equal to PQ, BC must be equal to QR, and AC must be equal to PR. Right? The corresponding sides must be the same length. SAS also works for congruency, except again, no longer looking at the ratios, we're looking at the actual lengths. The lengths must be equal and then the included angle must be equal. You can also use ASA, but remember here, the A, when you have two A's, automatically the third angle is equal. So this is really saying that you check that all the angles are equal, so you get similarity. And further to that, you find one of the pairs of sides have the exact same length. So it's like proving similarity and then saying, well, okay, this side, the side, for example, AB is exactly the same as PQ, so we also have congruency. Right? ASA and AAS are basically the same thing, right? It's just because again, once you have two angles, you automatically have the third. This is a special one here where you have the hypotenuse and any side of a right angle triangle. If you have two right angle triangles and they have the exact same length of hypotenuse and one of the corresponding sides, the other two sides is the same length for both, then automatically you could use Pythagoras theorem and get the third side being equal as well. So that's another thing you can use for congruency when it's right angle. So note AAA doesn't work because again, this only gives you similarity, it doesn't give you congruency, and similar to above, ASS doesn't work, right? Because again, you can draw two different triangles using that. All right, so now that we've covered that, I want to go back and look at the different lines in a triangle, because this is important that you know how to visualize and how to prove these things. So first of all, we're looking at perpendicular bisectors. So we say that a perpendicular bisector is a line that passes through the midpoint of a side and is perpendicular. Basically, it's perpendicular to the line and it bisects the line. That's basically what it is. Now we know, we told here that the three perpendicular bisectors of a triangle are all concurrent, meaning they intersect at a single point. And that single point is called the circumcenter, usually denoted by O. Now from the circumcenter, you can draw a circle passing through the three vertices of the triangle. So let me switch across here to the diagram now, so I can show you how this works. All right, I have some additional hidden stuff here that I'll show you as you go. All right, actually I should hide the circle because I don't want you to see that right now. All right, so what I have here is I've constructed the three, so I have a triangle A, B, C, right? A, B, and C. And I've constructed the three perpendicular bisectors. Now you all will have to do this when you're constructing a perpendicular bisector. You could basically open your compass or radius, right? To draw a circle here around point A. It should be larger than half the length of the line, the radius. Draw a circle around point A, a circle around point B with the same radius that you use. And then whatever 2 points intersect, you draw a line through that. And that will be the perpendicular bisector. All right, so let me show you. Let me do this quickly and then, or it's better if I use a fixed radius.
Are we ever required to do these kind of constructions for problems?
It'll help. There have been round 2 questions in the past where you had to do constructions like that. At the IMO level, not necessarily, but sometimes knowing how to construct these things is very useful. So let me give this a radius 5 because I'm not sure. Yeah, that's good. And I'll also give this a radius 5. So if I draw 2 circles, right, notice the perpendicular bisector passes through the points of intersections. So that's how you construct it. You draw the 2 circles, same radius about both lines, and then draw the line through the intersection points. Right, and you do that for all 3 sides, and that will give you the 3 perpendicular bisectors. Now, the question I'm going to ask you now is, well, how do you prove that they actually intersect at a common point? Well, so I have 2 of them drawn in blue and 1 drawn in red. So let me ignore the 1 drawn in red for now. Right? So I'm going to take the perpendicular bisector of AB and BC and let the intersection of those 2 lines, obviously they're not parallel, so they must intersect, right? And it is impossible for them to be parallel because that would mean that AB is parallel to BC, which doesn't make sense. It basically would just have a straight line. So yeah, they intersect, so we'll call that point of intersection O. Now what I have to do is I have to show that the 3rd perpendicular bisector passes through O, right? So let me not draw that for now. All right, so what I'm going to do is I'm going to connect A to O, connect B to O, and connect C to O. All right. Now, it'll help if we know what the end result we're trying to do here is. Now, remember, as I mentioned, from the circumcenter, you can draw a circle passing through the 3 radii. The 3 vertices. So if there's a circle passing through these 3 vertices and O is the center, then it should mean that AO, BO, and CO are radii. So they should be equal in length. So we're going to try to use that fact or try to show something about that fact. Now, so I've connected AO, BO, and CO. Now notice that O lies on the perpendicular bisector of AB. Right? Now, any point on the perpendicular bisector of a line will be equidistant from the 2 endpoints, meaning that AO must be equal to BO because of the fact that this is a perpendicular bisector. You can think of this as an isosceles triangle. All right? Is that not clear to anybody? That if I have a perpendicular bisector, I choose a point on the line, this is just O is just a point on this bisector, right? So I choose a point there, and then automatically AO must be equal to BO. So we know this is a perpendicular bisector, right? So if I call this point here X, I know AX is equal to BX, all right? And I know XO is common to both triangles, and the included angle is 90 degrees for both of them. So automatically these two are congruent. And because they're congruent, AXO is congruent to BXO, it means that the third side must be equal. That's by SAS. So you could actually prove it if you wanted to, right? But AO is equal to BO because this is a perpendicular bisector of AB. Similarly, if I consider this perpendicular bisector, it means that BO would be equal to CO because O lies on this line, this bisector. So I have that AO is equal to BO and BO is equal to CO. So automatically AO is equal to CO. It means that O is equidistant from A and C. And what that means is that O lies on the perpendicular bisector of AC. Because the only points that are equidistant from 2 points are the points that lie on the bisector, perpendicular bisector. Is that unclear to anybody? Okay, good. The key here is you can't start off assuming the 3 points are concurrent, right? You choose 2 of them, 2 of the lines, you take that point of intersection and show that that point of intersection lies on the third side. That's how you usually do questions like this, or the third line. Now, as I said, these are radii, so you could draw a circle passing through the 3 points. All right, and this circle is called the circumcircle, or sometimes the circumscribed circle. Now, the radius AO, BOCO is called the circumradius, which is capital R. And sometimes if you do things like, if you look at the extended sine rule and those things, it involves, some of those things involve capital R. All right, what I want you all to do, so these proofs that I'm explaining, I'm not actually writing them down. I'm actually explaining them visually. I want you all to write them up properly. So all of these things, the proofs that perpendicular bisectors, medians, altitudes, and angle bisectors, the proofs that they intersect a line, and also whatever is given here, I want you all to write up formal proofs for them based on what I've shown you. So I hope you're paying attention. Right, now there are things that you can do with the circle, and there are many questions that involve it. So you need to know what it is. You need to know how to find the circumcenter. Right, key thing with the circumcenter is basically it's equidistant from the 3 vertices, and it passes through the bisectors, perpendicular bisector. Well, it lies on the perpendicular bisectors of the 3 sides. Okay, the next one here is the median. So let's look at that one. 3 medians. Right, now this one I have some more, the proof for this is a little more complicated, right? So it'll be a little more work to show you. So suppose I have, again, a triangle ABC. Oh, one thing I should have shown you before. Let me just briefly go back to the other one. Now, I've done this for this triangle, right? But I could actually move around the point C, and you'll see that no matter where I move the point, the 3 lines always intersect at a common point. Right? It's not that I've defined lines to intersect there, it's just that they always do. Also notice, right, if I have C somewhere up here, it's fine, the circumcenter is inside the triangle. But if I pull C this way, the circumcenter lies outside, in which case this thing has an obtuse angle. Right? So it is not necessarily the case that the circumcenter has to lie inside the triangle, so be careful with that. Right, and I could pull C down here and then it goes up there. I could do whatever I wanted, but it is always like this. What happens if I do this? What can I say about this triangle if the circumcenter lies on a side?
The angle ABC is 90.
Correct. So this is one thing you want to watch out for. If you see something like a right angle triangle and you take the midpoint of that side of the hypotenuse, then if you're given that as a right angle, right, this means automatically that AO is equal to CO is equal to BO. Right? Because it basically there's a circle passing through the three vertices and O is the center of that circle. So it means that AO, BO, and CO are all radii. So that's something to watch out for. That was in one of the questions on the selection exams. All right, now let's go on to the medians. So I have, again, a triangle ABC. I choose the midpoint, right? A median is basically a line joining a vertex to the midpoint of the opposite side. So D is the midpoint of AB, and similarly E and F are defined as those midpoints. Right, let me remove the red one. So I'm going to take the medians AE and CD, and I'm going to let those intersect at a point, and I'm going to call it G, which is the notation for the centroid. So I have that these two lines intersected at this point G. What I need to prove is that the third one, BF, also intersects at G. Now, how I'm going to do this is a little bit of a roundabout way compared to before. First, what I'm going to do is I'm going to define 2 points. I'm going to define M and N as the midpoints of AG and CG respectively. Right? Now, the motivation for that is the fact that it was stated here, the centroid, if D is the midpoint of BC, well, okay, this one is probably better. The centroid trisects each median, meaning that what happens is that if this is the centroid, it basically divides this median in the ratio 1 to 2. So that's why I'm going to define these points as midpoints. So basically what I have is that DG would be equal to GN would be equal to NC. Now, I don't actually know that yet, right? I'm trying to prove that. So I'm defining these points as the midpoints of AG and CG, and I'm going to try to prove that in the end. All right, what I'm going to do now is I'm going to connect M and N. I'm going to connect, well, these 4 things. All right, M, N, DE, MD, and NE. Does this look interested in any way? If you were just to look at this, what conclusions you might try to draw from it?
Maybe some sides are parallel.
Yeah, correct. So how can we do that? Well, what do we know about D and E? How are D and E defined?
They were midpoints.
Correct. They are midpoints of, let me zoom in this a little bit. D and E are midpoints. What special theorem did you see with midpoints?
The midline theorem or something?
Correct, the midline theorem. If D and E are midpoints of these 2 sides, then this line DE is parallel to AC and is also half of the length.
Oh, you would have had to like kind of.
Remember, F is a midpoint, right? So it means that DE is equal to AF and also equal to FC. Right? Now, similarly, consider triangle AGC. M is the midpoint of AG and N is the midpoint of CG. So in triangle AGC, we have the same thing happening. MN is parallel to this side and is equal to half of the length. It follows from that that MN is equal to the length of DE and also parallel. Is that clear?
Wait, why are they equal?
Because they both equal to half of the side.
Oh, okay.
They're equal to the same thing basically. So they must be equal to each other. Right? So based on this, we have that MN is parallel to DE and equal to half of the well, they equal to each other. Both of them are equal to half of the length of AC. Is that enough to conclude that DENM is a parallelogram? Well, the answer is yes. We haven't actually done it yet. So, but it is one of the conditions. So to prove something is a parallelogram, one way to do it is to prove that a pair of opposite sides are both equal and parallel. Right? So there are several ways you could prove that the opposite sides are equal. So this is equal to this and this is equal to this. Or the opposite sides are parallel. This is parallel to this and this is parallel to this. But there's also a third way where you say you just choose one of the pairs and say they're equal and parallel. Automatically, the other one will be equal and parallel as well. Yeah. You could actually prove it if you wanted to, but we're not going to bother with that. We know that this thing is a parallelogram. It means that NE is parallel to MD. Yeah, because it's a parallelogram. So NE is parallel to MD. What does that tell us? Does it tell us anything?
I would say some angles are equal, but I wouldn't see how that's helpful.
Okay, yeah, it does. It would give you some equal angles, but we're not focusing too much on the angles here, more on the lengths and so on. Remember what? Okay, this is parallel to that. Well, this is a parallelogram. What do we know about parallelograms in terms of the diagonals?
They bisect each other.
Correct. They bisect each other. It means that even though we didn't actually remember, we didn't know before. Well, we knew it, but we didn't prove that DG was a half of this length. But because the diagonals bisect each other, it means that DG must be equal to GN. But GN is equal to NC based on the definition of N. N is the midpoint. It means that G is such that this length is a half of this length. Or another way to say it is to say that G trisects this side. Divides it in the ratio 1 to 2. And similarly for this, right? EG would be equal to GM, but we defined M as the midpoint of AG, so automatically G trisects AE. Right, so based on what we have there, we know that the intersection of these two is 1/3 the way up CD, right? The intersection is fixed, is 1/3 along the line CD. Well, DC if you want to go that way. What I'm going to do now is, where is this? I'm going to take off AE. And we can do the same thing with these two, or something similar with these two medians. Right? I'm not going to go through it, but you could define the midpoint of this side here, of BG. You construct your quadrilateral, and then it shows a parallelogram. And from that, it would follow that, now, if you're doing it with these two, right, you can't use this point G here anymore. So if I use these two, what I would need to do is call it something different. Let me call it G1 or G prime. The key here is you can't assume it's the same point G, because you're trying to prove that all three are concurrent. So if I take this one and intersect it with this one, which I didn't have before, then I can't call it G anymore. I have to call it something else. So I'll call it G prime. Now we can go through the same analysis we did before by defining the midpoint of BG prime and then constructing the quadrilateral, showing us a parallelogram, and showing that G prime lies 1/3 the way up DC. But if G prime is 1/3 of or the way up DC, and G is also the same, defined the same way, it means they must be the same point. It's impossible to have two different points that lie in the same position. So that's how you prove in this case that the three medians intersect at a point. Basically, you take two of them, take the intersection point, show it lies at a specific point on the medians, and then you take the other median with one of these and then show the same thing.
When you have such symmetry in a question, like how
Only when it's
you said, like,
obvious. This case, it would not, you can't use symmetry because like I said, you don't know that they intersect at the same point. So symmetry wouldn't apply.
oh, okay. But if you do have symmetry in a question, can you just like you do one case and then say
If it's
it applies?
obvious, then yeah. For example, if you had an isosceles triangle and you work on one side of the triangle, then you could say by symmetry it holds on the other side.
Okay.
Assuming it actually did hold. You don't actually have to go and explain everything again. All right, so that's in medians. All right, so we're done with this one. The next one is altitudes. Now, altitudes is gonna be a little, this is gonna be a weird proof. It might confuse you a little bit. So how the altitudes are defined is if I have a triangle ABC, an altitude is a line from a vertex that is parallel to the opposite side. So this has to be 90 degrees and it must pass through the point C. It's similar to a perpendicular bisector. It's shifted a little bit. The perpendicular bisector would have been parallel to this, but it would have passed somewhere here through the midpoint. Right? So we draw the three altitudes and they intersect at a point called the orthocenter H. Notice unlike the previous ones, I have all three in the same color here. None of them, I didn't put any in red. And the reason being, the proof for this is gonna be very different from the other two. So I know that the altitudes, so for the time being, let me ignore H. We don't know that they intersect at a point, right? I'm just gonna draw the three altitudes and we don't care whether they intersect or not right now. Now the altitudes are perpendicular to the sides. So that's the thing to bear in mind now. What I'm gonna do is I'm gonna draw some parallel lines. I'm gonna, through the point E, I'm gonna draw a line parallel to BC. Right, well that's the other one. So I'll do it for all three sides. So through the point A, I've drawn a line parallel to BC, and then through the point C, I have a line parallel to AB, and similarly through the point B, I have a line parallel to AC. Right, that's your red ones. So we draw three parallel lines here, and let's call the intersections D, E, and F. So D is the intersection down here, E up here, and F up there. Okay. Can I say anything about the altitude through B with respect to the line DE? Do I know what this angle is? The angle DB, well, going this way.
Yeah, it should be 90, no?
Yes, it is. And the reason being is that, remember, AC is parallel to DE, or DE is defined as being parallel to AC. So this is parallel to this, and this altitude passes through the two lines, and this angle here is 90. It means this angle must also be 90. Yep. Right, so think of it this way. You have two parallel lines and a line cutting them. This line is perpendicular here. It must also be perpendicular here. So this altitude is perpendicular to this. And similarly, the other two will be perpendicular to those sides. So that's one part of it. So we've shown that the altitudes are perpendicular to the sides of DEF. Now, what I want to do is, there are a lot of lines in here, right? Let me remove the altitudes for now because they kind of complicated things. I know the altitudes are perpendicular to the sides. Consider A, B, C, E. What does that look like?
Parallelogram.
Correct. And it is a parallelogram because AB is parallel to CE. Remember, this line is defined as being parallel to AB. Similarly, this line is parallel to this. So the opposite sides are parallel, which means it's a parallelogram. And because it's a parallelogram, AB is equal to CE. Yeah? So I know that AB is equal to CE. Now consider this side here. ABCF. Same thing happens. AF is parallel to BC. CF is parallel to BA. So again, we have a parallelogram here, which means that AB must be equal to CF. So AB is equal to CE and AB is equal to CF. So both of these are equal, which means that C is the midpoint. Is that clear? So C is the midpoint of this side. Similarly, B is the mid. You could do the same analysis here. Now, this is where you could say by symmetry, right? Or not even by symmetry. You could say without loss of generality, they would all it would also apply down here and across here because we haven't assumed anything specific to the point here or anything that doesn't hold on this side. So we could do a similar analysis and show that AC is equal to BE by considering this, and then also consider this and show that AC is equal to BD, and then therefore B is the midpoint of DE. And similarly, A is the midpoint of DF. So what we have is that A, B, and C are the midpoints of the sides of DEF. And these lines are perpendicular to the sides passing through those midpoints. So what are the blue lines with respect to triangle DEF? Remember, the blue lines are perpendicular to the sides and they pass through the midpoints.
Perpendicular bisectors.
Correct. So what we have here is so we start with triangle ABC and we constructed a triangle DEF such that the altitudes of ABC are actually perpendicular bisectors of DEF. And what did we prove about perpendicular bisectors?
They intersect at the same point.
Correct. So this is like it's like an indirect way of proving it using something else we know. So we know that the perpendicular bisectors of DEF intersect at a common point. It means that automatically the perpendicular the altitudes of ABC intersect at a common point. Right now, I could actually move this thing around, move the point C around, and you'll see the triangles change. Right, the orthocenter does not have to lie inside a triangle. It can lie outside. That is just going to be a little confusing, so let me not play around with this too much. There are some relationships between the orthocenter and circumcenter and those things. Those are a little more advanced, so we're not going to go into those things here. All right, so we've done these three. The last one is angle bisectors, and these are you can do a lot more things with these. Okay, I didn't draw this one in red. I put it as a dotted line because I have, as you can see, I have a bunch of different things hidden here that I have to show you all. Okay, so where do we start? What is that? Okay, I'll figure it out as we go. All right, so again, I have a triangle ABC, and I want to prove that the three angle bisectors intersect at a common point, which is called the in-center eye. All right, so for the time being, we're just gonna take two of them, and we're gonna let the intersection points of these two angle bisectors be I. Now, remember, it's an angle bisector, so the angle BAI is the same as the angle CAI, right? And similarly, CBI is the same as ABI. I didn't draw it here, but this angle is this, and this angle is this.
Wait, could you just repeat that?
Sorry?
Could you just repeat that? You said something about CBI is...
Remember, this blue line, this line down here is an angle bisector of ABC. Yeah. It means that this angle here is equal to this.
Oh, right.
And this angle here is equal to this. I didn't actually put in the angles, but they're equal. So CAI is the same as IAB. And CBI is the same as IBA. based on what the lines are. The lines are drawn so that they divide the angles in two. All right, not that yet. All right, what? How did I get that? Okay, no. So what I'm going to do is we're going to go through this in steps, right? So I have this triangle. I take two of the angle bisectors and intersect them. What I'm going to do is I'm going to draw a line through that angle bisector that is perpendicular to the side down here. So basically drop a perpendicular to the side, and I'm going to let that point be D. Right? So D is a point on AB such that DI is perpendicular to AB. All right, not time for that yet. Similarly, I do the same thing up here. All right? And do the same thing across on the side. All are defined in the same way. So EI is perpendicular to CB and AC is perpendicular to IF. All right, I don't need a line, so I have that. All right, and I connect those. I probably should have erased that, but having all of these lines is probably going to get a little confusing. So let me remove those and let me connect these separately. All right, there's no time for that yet. Okay, so this is what I have, right? So I know that IA is an angle bisector, so angle DAI is the same as FAI. Yeah, and similarly, EBI is the same as DBI. Now, one thing to note here is that this angle, I didn't put it in, but angle AFI is 90. Right? And ADI is 90. So both of these are right angle triangles. Now, one way to prove congruency for right angle triangles is to prove they have the same hypotenuse and a corresponding side is the same length. Can we do that here?
It looks like it. The same hypotenuse, and I can't say that. I can't say that ID is IF.
Well, okay. In this case, you would have to treat it not like a right angle. Just use one of the proofs for congruency. So remember, AI is an angle bisector. So this angle here, do I have the angles drawn anyway? No, I don't. So angle FAI is the same as DAI, right? And angle ADI is 90 and angle AFI is 90. It means that this angle here is 90 minus, I could call this, let me call this angle FAI alpha. If this is alpha, then this is alpha here. This is 90 and this is 90. So this is 90 minus alpha and 90 minus alpha. So both of these triangles are similar, at least. Yeah? They have the same angles. Angle AFI is similar to ADI because they have the same angles. Now also AI is common to both. So they're similar, but they're also congruent. Is that unclear to anybody?
You define ID and IF to be perpendicular, right?
Yeah, we define DE and F to be perpendicular. So we define them so that this is 90 and this is 90 and this is 90.
Right.
Right, and we needed that because if we didn't know that, we couldn't do what we're going to do now. So this angle is this angle is that, so they're similar, and then AI is common to both triangles, so they have a common side, which means that they're congruent. Basically, if I reflect D in the point AI, it'll fall on F. Exactly. D on the line AI. Yeah, so it means that ADI is congruent to AFI. And because they're congruent, it means that DI must be equal to FI. Yeah? Is that clear? All right? So DI is equal to FI. We could do the same thing across here. If I let this angle be beta, right? Angle EBI be beta, then angle DBI is also beta. But this angle here is 90 and this angle here is 90. So both of these are 90 minus beta. So these two triangles are similar as well. And they also have the same corresponding side. BI is common to both. So therefore both triangles are congruent and it follows that DI is equal to EI. Now what we have is that FI is equal to DI from the first one, and now DI is equal to EI. It means that FI is the same as EI. Now if FI is the same as EI, right, and this is 90, this is 90, this is, remember, so, okay, the key thing here is we don't actually know yet that this is equal to this. Remember, we only assume that the angle bisector here intersects with the angle bisector here. Well, not assume, but we let I be that point. If I connect I to C, I don't necessarily know that this angle is this angle. I have to prove that. So what I have now is that this is 90, this is 90. This side is equal to this side. And I have a common side here. Can I do anything with that?
Yeah, it's the same as before, no?
Sorry? Well, it's not the same as before because before we knew the angles were equal up here.
No, but you have side 90, and yeah, you have two sides and the non-included angle, I think.
Right, non-included, that's the key thing here. It has to be included if you want to use that.
No, but two sides and a non-included angle, isn't that congruency?
Let's see. Two sides and an included angle, but there's nothing with two sides and a non-included. That doesn't work.
All right, okay.
So how do we finish this? I heard a voice here, so. So this is equal to this. This is 90, this is 90. CI is common to both. Can we conclude anything from that?
Oh, you have a leg. No, actually, don't worry.
Wait, can't you just, since it's a 90-degree triangle, you could just say that since you have two sides that are equal, you use Pythagoras to say that CF and CE are equal, and then you use...
Yeah, well, so yeah, you're correct, but you don't actually need to go all the way there. It was here. Version has go up. This one. This is the hypotenuse. That's common to both,
yeah.
And they have a leg common to both. So they must be congruent.
Right.
And because they're congruent, it follows that this angle is equal to this angle. And from that, you get that I, which is the intersection of these two angle bisectors, also lies on the third angle bisector. So in other words, the third angle bisector intersects each of the others at the exact same point. And that's it.
Wait, could you repeat that part?
Which part?
That CI lies on the same point as the other two where they intersect.
No, well, so what we've done is we've taken the point of intersection of these two angle bisectors I, and we've shown that this angle is equal to this angle. If I connect I to C, it means that I lies on the angle bisector of this angle.
Right.
It means that the angle bisector of this angle intersects the other two at the exact same point.
Oh, okay. Cool.
Yeah.
Also,
yeah.
Knowing that FI, IE, and ID were equal.
Yeah, so because they're equal, you could draw a circle. which is called
And then
circle.
do you have a using tangent theorem to say that FC is EC?
FC is equal to EC.
Yeah. Like two tangents to a circle that
Yeah,
intersect.
you're correct. You could do it that way as well.
Cool.
That's pretty well. Either way, it works out.
Yeah.
Right. So you're right. Because these three are equal, we could draw a circle centered at I. And because this angle is 90 for all of these angles here, it means that that circle is tangent to the inside of the triangle at all sides. Right? And this is called the in circle. The radius of the in circle is normally denoted common R. Now, there's actually a formula for the area of triangle. If I wanted the area of the triangle ABC, you all would have seen Heron's formula, right? Which uses semi-perimeter. Basically, square root of S by S minus A by S minus B by S minus C. Well, this is A, this is B, and this is C. If you know what the in radius is, the area of the triangle is just R times S. You don't have to worry about any square roots or anything. So basically, the area of this triangle, if you knew what the in radius is, if you know what DI is, the area would just be DI times this side plus this side plus this side all divided by 2. You could try proving that if you want. Okay, now I had mentioned last time, but we didn't actually go into it, that there are also things called X centers. This is an in center. Things called X centers and X circles. So what I'm going to do is I'm going to extend all of these sides. Right? Which one do I start with? I'll start with A. So let me not extend this one yet. Right? So I'm extending AC and AB. And let me take out some of these things because they might get confusing. All right, we're done with D, E, and F. We don't care about those anymore. All right, let me draw back the angle bisectors. All right, for the time being, that's the only one I need. All right, so I'm going to take the angle bisector passing through A. I'm going to extend the side AC, and I'm going to take this angle BC with whatever point this is, this angle here, this obtuse angle. I'm going to bisect that as well. Let me see if I find the correct line here. Where is it? Oh, it's up here. Right, so this is the line. So if I bisect this, I'll get this line, this red line here. And let me bisect this angle down here as well. Now, if I do that, right, I take the angle bisector from A and I extend these lines and I bisect the outside, the angle on the outside of the triangle for the other two. Right, they're on the outside of the triangle, but they're within these two. You can think of this AB extended, AC extended, everything is going to be inside here. So you're bisecting this angle and this angle. And all three of those lines, the two external angle bisectors and the internal one for A would intersect at a common point, which is called the X center. And because it's opposite A, it's normally called the X center I subscript A. Right, so there'll be one for B and C. So I subscript B will be here, I subscript C will be down here. Now, let's see. All right, there's actually a circle from I. There's a circle passing through, well, centered at IA that is tangent to all three of these sides. So it's tangent to BC and it's tangent to the extensions of the other two. And that's called the X circle. It's outside the triangle, but it's still tangent to sides or extensions of sides. All right. So I could do the same thing for the others. This is gonna get really a lot of lines gonna get involved here. All right, just give me a second. Let me figure out what I'm trying to do here. Not this one. That would be this one. Okay, no, it's just that. All right, so this circle here is tangent to the extensions of AB and BC, and it's also tangent to AC. Similarly, this one is tangent to AB and the extensions down here. And they all intersect at common points.
The diagram looks like an IMO solution.
Yeah, basically. Right, now how you would prove those is similar to for the in center, right? So what you would do is let me remove some of these things and show you just one of them. All right, what else do I need to get? Don't need B, I don't need C. I need that, don't need that. I need that, which is the one I don't need. This one, I don't need this one or this one. All right, that seems a lot nicer. All right, so how I would prove this is, let's see. Where did I have this point? Not that one. Yeah, so what you do is from this, so you could let, for example, just for simplicity, let me remove the blue one. All right, so you let these two lines intersect at IA, then you draw perpendicular to this side, right? And a perpendicular to that side. I don't think I labeled those points, did I? Should have, but I'm not seeing them. I don't think I did it on this side, it's on the other side. Anyway, so you draw that line. And you draw, why is this the same line? I don't know what's going on with that. All right, it's getting all confusing now. There's too many things. But basically, you draw a line perpendicular here. You define this point. You draw a line perpendicular here. You define that point, and same thing. Well, same thing here. And you basically go about doing the same thing that we did before, except now the circle is on the outside, or the point is on the outside. But you would get you would have the same kind of approach that you would use for the circle on the outside. Similarly for the other two. What I want to do is I want to remove the bisectors and this weird line. Where is it? Yep. Right. So if I move, I should also put in the in circle. Right, so I can move this thing around and you'll see how the circles change, right? Circles either get very big or very small. But the ones on the outside will always be bigger than the one on the inside. All right, I want to zoom in a little bit here and show you something now. I'll remove the circles because they kind of annoy now. I need to add back. I don't understand what KL and L are working. All right. Okay, so you see these points here? Not these. Let me make it a little more scaly. Okay, right. You see this distances here, AD and AF? We know they're equal, right? Because these are tangents. But I can actually tell you what AD is in terms of the overall lengths. In terms of, so if this is A, this is B, and this is C, right? Remember, the semi-perimeter S is A plus B plus C over 2. This distance AD is going to be S minus A. Similarly, AF is going to be S minus A. They're equal. This distance BD is going to be S minus B. Similarly, here is S minus B. And this one, CF and CE are both equal to S minus C, where, again, it's the opposite side. Right? I want you all to try to prove that as well. So you're trying to prove that AD is equal to S minus A, BD is equal to S minus B, and CE, or whichever one is equal to S minus C. Sometimes when you have in circle and you deal with the tangents of the in circle at the sides, it's useful to use those relationships. All right, so that's more homework for you to try. All right, any questions on the in circle or the in radius or anything like that before we move on?
Just a quick question, right?
Yeah.
So you have the points IA, IB, IC, and I want to know if there's any relationship between those points and the actual ABC. If there could be, or if there is any relationship between.
I am not sure. There might be, but I don't know of any. If you want, you could try to derive some kind of relationship. So you connect I, B, and C, I with I, B, and C. You could find that length in terms of A, B, and C.
Okay, no problem.
I feel like, look at it, right? Like IB is going up way too much as these don't increase much. So I feel like there might not be, but you could try. What there might be is a relationship with the overall lengths, like this length plus the other one, right? There might be some kind of relationship with that. Because as one increases, the other one would decrease. That went way too high. So maybe it's not a linear thing. It might be a multiplicative thing. You can try to figure out if there's one. Like I said, I don't know.
All right, thanks.
Yep. All right. Next is trigonometry. I'm not gonna go into this too much. So in a triangle, there's a sine rule you all know, but like I said, there's an extension to it where this ratio is actually equal to twice the circumradius. Right? Circumradius is the radius of the circumcircle, not the incircle. Cosine rule is useful sometimes. Pythagoras, everybody knows. This one here, angle bisector theorem. I should have done something with that. Oh, actually, I should not. All right, angle bisector theorem. What's the theorem say? In a triangle ABC, if D is a point on the side BC such that AD is an angle bisector, either internal or external, then you have that ratio. Okay. So let me construct an angle bisector here. Now, for me, it's easy using a software. For you all, it's not necessarily going to be easy. All right, I'm going to intersect it. All right, so that's point D. I no longer need that line. And actually, I really don't care about what this angle is, so let me really delete this. All right, so angle bisector theorem says that if this is an angle bisector, if CD is an angle bisector, Is it CD? Nope. I need to move these points around. So I need this to be okay, that's better. All right, so I have a triangle ABC and D is on the side BC. All right, so AD is the angle bisecting. Basically, it means that this angle here is equal to this angle. Now, what this theorem says is that if that is true, then BD, what's that? BD divided by CD is equal to AB divided by AC. So this segment BD divided by CD is the same as AB divided by AC. That's only true if this is an angle bisector. Now, how you could prove that is actually using sine rule. Right? Is it done here? No, it's not done here. But you could prove that using sine rule. So you let this be 2 alpha, so let this be alpha and let this be alpha. And then you use sine rule in triangle ACD, right? And then use sine rule in triangle ADB. And then overall use sine rule in triangle ACB. Actually, is it sine rule or cosine rule? It might be cosine. Cosine rule might be more useful because you don't know what these angles are. So use cosine rule instead. Use cosine rule with triangle ACD, ADB, and then ACB, and you'll get cos 2 alpha here, and then you'll have to use double angle formula. And basically use that to get a bunch of different ratios, and then try to show that BD divided by CD is AB divided by AC. So that's what we'll be able to try to do. All right, like I said, there's another formula here. If common R is the in radius, then the area of the triangle is also R times S. And that I want you all to try to prove as well. All right, these are not going to spend too much time on. That question that you all had, the geometry question, you needed this to be able to solve it, right? So knowing these things can be useful. All right, quadrilaterals. I'm not going to go too much into this. We've talked about this already a little bit, how to show when something is a parallelogram. Rhombus is similar to parallelogram, except that these sides, the opposite side, well, all the sides are equal. Yeah, and that many, I guess, parallelogram or quadrilateral theorems. Most of them are kind of straightforward. The circle ones, we'll go in, we look at a little more detail. So where do I start?
Yeah, question.
Yep.
In the fundamentals PDF.
Yeah.
Above, there is a question that had a strange proof where you had to, yeah, that one, where you had to construct that X and Y to be intersecting points, basically. Where do you get the motivation to do something like that?
Yes, let me read the question. Quadrilateral A, B, C, D, such that angle A, C, is twice this one up here. And then this one is twice that one up there. Okay. And CB is equal to CD. Show that CAB is CAD. That would be the same as showing this is equal to this. Okay. All right, let X be the intersection of AB and CD, and Y be the intersection of AD and BC.
Like, is the intersection thing a standard trick, or was this?
Yeah, I mean, usually it depends on, it varies from question to question. Sometimes you extend lines, sometimes you introduce midpoints, sometimes you introduce intersecting lines, or you might introduce altitudes or anything like that. I mean, in this question, you could also try introducing angle bisectors because this is twice that, but I don't think that'll help necessarily. So if you let this be an angle bisector here, you would get an isosceles triangle basically, because actually you wouldn't. If you use an angle bisector here, then they would be parallel because you would have corresponding angles, alternate angles, that's what I'm thinking of. So this would, if you introduce an angle bisector, that would be parallel to this, and similarly, that angle bisector would be parallel to ED. None of that is explaining why you would introduce X and Y as here. I think this is a more complicated one. Sometimes it's straightforward, sometimes it's not, and this is an example where it's not straightforward. Yeah. What you could do is try to do it that way that I mentioned. Try to see if the angle bisectors help because
no problem.
They seem like they could. All right, so we're gonna go through these, some of these. So the first one is Thiel's theorem. All right, that's straightforward. It says if you have a diameter of a circle, AB, is it AB? Okay, this is the opposite. This has AC, but just pretend this is what we have. So AB is a diameter, and then C is an X point on the circle. That angle ACB is always 90 degrees. All right, doesn't matter where it's in. You could prove that if you connect O and C. If you connect O and C, then this thing here, well, these are all radii. AO, CO, BO are all radii. So, yeah. So this is isosceles, which means that this angle is that angle. Similarly, that is isosceles, that angle is that angle. Now the sum of all the angles in here should add to 180. So 2x plus 2y should be 180. It means that x plus y is 90, right? But notice I have x plus y here. So this must be 90. That's basically how you prove Thiel's theorem. It's straightforward, but this kind of approach usually helps with things involving circles, kind of breaking up the angles. So you use the fact that radii, that if you have radii, it'll give you isosceles triangles. Right, the next one is angles at the center and angles at the circumference. So basically, first part of it is if you take a chord and you connect the two endpoints to the center, and then you connect them to another point in the circumference, this angle at the center will always be twice that angle on the circumference, right? Unless the angle is on this side. If it's in the alternate side of it, then basically what you do is you have to go on to the opposite. It would be 360 minus this would be twice this. Right? Always make sure it's on the same side. And as I move it around here, notice it's always the same, no matter where it is. So that's another one. If you have a chord AB, it always projects the same angle on the circumference, no matter where on the circumference it is. Right? Except if it's down here. If it's down here, it will be 180 minus that. All right, what? There was a second thing I was going to say here. Hopefully I'll remember after. All right, first of all, we'll prove that the angle here is twice the angle there. All right, don't need those angles to be for the work, but I'll just leave it on for now. So again, connect OC. Then these are all radii, right? So you have 3 isosceles triangles going on here. What is it? Oh, this is something else. I'll explain this. That's what I put. What is this? Okay, I don't know why I have these things there. All right, I don't have the angle specifically here, right? But if you let this be x, then this is going to be x. Let this be y, then this is going to be y. So this angle is x plus y. All right. Now, if this is x and this is x, then this angle AOC is 180 minus 2x. And if this is y and this is y, then BOC is 180 minus 2y. Right? Because angles in a triangle are 180. So I have 180 minus 2x, 180 minus 2y. The sum of those is 360 minus 2x minus 2y. It means that this one must be 2x plus 2y because the total sum has to be 360. So this is 2x plus 2y, and this is x plus y. And that finishes the proof. All right, so what I proved there is that the angle at the center is twice the angle at the circumference. Now, you need to be careful with that because the converse is not necessarily true, right? That's what this other thing was I had here. If I give you a point D, and I tell you the angle ADB is twice the angle ACB, it does not imply that D is the center of that circle, right? As you see here. D could actually, I mean, one point that satisfies it is, yeah, is O, fine, but it could be any point here and it would still work. Reason being is it would work as long as A, B, D, and the center of the circle lie on a common circle. Because this angle would always be equal to this angle, right? Angle subtended on the circumference is the same. So again, be careful with that. If I give you, let's repeat that. If you have 4 points such that ACB is a half of ADB, it does not imply that D is the center of the circle. All it implies is that A, B, D, and the center lie on a circle. All right, let me remove these things now. All right, next thing is the angle. Well, once we show that the angle of the circumference is twice this, then it doesn't matter where this point is. It will always be the same value. Now to prove that, oh, actually, almost forgot. This proof that I did here is not a general proof, right? The reason being, this is only one particular case where I show that this is x plus y and this is 2x plus 2y. That is only in the case when O is inside the triangle, ABC. If the center is not, if C is such that the center is not inside that triangle, then you have to be careful. Because now this line is outside. Right? So you'll have to adjust the proof. So I want you all to consider to see how the proof would change in that case. It would be very similar, but a slight difference. There is a third possibility when O lies on the side BC, but that we've already covered in Thiele's theorem. Because in Thiele's theorem, this is 90 and this is 180, so it follows. Actually, I said that wrong. It's supposed to be this way when AB is the diameter. Right, then it'll be 90. Right. So case 1 is with Thiele's theorem. Case 2 is when it's like this with O inside. Case 3 is when O is on the outside on either side. And then case 4 is this. Right, where it's in the alternate segment. Not alternate segment theorem, but still in the other segment. In this case, the angle would be the big angle up here, not the small one. And this angle, so this is 126 point whatever. This is rounded off, right? Basically, if you take twice that, you'll get the big angle up here. So it still works, but you have to show it slightly differently. All right, so that covers these two cyclic quadrilateral angles add up to 180. So just 2 more we'll do and we'll kind of close off geometry. So a cyclic quadrilateral is something that where a quadrilateral whose vertices lie on the circumference of a circle. To prove it's cyclic, you connect the diagonals, right? And then you use the fact that the angle subtended by the chord is the same. So if this is angle X, then that is also angle X because they both subtended by the chord AB. Similarly, if that's Y, then this thing down here will be Y. If this is Z, then this one up here will be Z. And if this is W, then this one down here, the last one will be W. All right, and now notice I have two X's, two Y's, two Z's, and two W's. And the sum of all of this must be 360. So I'll get X plus Y plus Z plus W is 180. But here I have X plus Y plus Z plus W on the opposite angle. So these must add up to 180. Similarly here, these must add up to 180. And that's basically the proof of it. There's another thing that I wanted to mention that I forgot to. Right. So we know that the angle subtended by this chord AB is the same no matter what the point is, right? If I put C here or I put C across here, it's still the same angle. There is another related theorem that is not stated here, I think. Yeah, it's not stated here, but basically what it says is that if I have a chord AB of length X, and I have another chord CD or PQ or whatever of the same length X in the same circle, both of them would subtend the same angle, subtend the same angles, right? So basically, if I have AB here, right, and I have an angle 54.13, let's say AB was 5 centimeters on the circle. If I take another chord CD somewhere else that is also 5 centimeters, it will subtend the same angle. So equal chords subtend the same angle, basically. Right, and that one you could think of it. That one kind of makes sense logically, right? Because you could just rotate the circle until the chords line up, and then the angle must be the same. The last one is the alternate segment theorem. Right, so you have a tangential circle, you have a chord AB. The angle made between the tangent and the chord is the same angle in the alternate segment of the circle. Meaning that this point C can't be the same side in the same arc of the circle as A and well, the smaller arc close to the tangent. It has to be on the other side of the line AB. Right, so that's one thing I should have mentioned as well. Sometimes you might see questions talk about arcs of a circle. So sometimes a question might define a point. So if I consider this line AB, right? This is a segment AB, but there's also an arc of the circle AB, which is a smaller arc here, and a larger arc AB here. Sometimes a point might be defined on an arc of a circle. So if I might say, let D be a point on the arc, on an arc of the circle AB, not containing the point C. It means that D has to be on this side. It can't be anywhere on this side because on this side contains the point C. So you have to look out for things like that. All right, but yeah, basically, so we have a tangent, we have a chord, the angle made between the tangent and the chord is the same angle up here, no matter where I put this. All right, and if I change, I'll have to change this. If I change the chord, the angle keeps changing the same way. Why is that? All right, so you could try to prove this one if you want as well. To prove it, you'll have to connect O to A. All right, and again, it depends on where this is, but because we have other theorems before we could use it. If you connect this, call this angle alpha, this would be 90 minus alpha, right? And well, what would you do that? Try to think of if you do need to connect O to A to actually be able to prove this. Okay, drawing a blank here. Anybody sees how we could prove this? This angle is equal to that angle. An easy way. There are plenty long ways you could find.
What if you connect OA and OB, and then you could say that angle AOB is twice the ACB,
Okay.
and then you
This
know,
angle is twice. What am I doing?
right, and then you know that OA, well, A is a tangent to OA, so it's 90 degrees here.
So this would be 90 minus alpha. This is 90
Yeah.
minus alpha. So this should be 180 minus 2 alpha. You're right. And then it should be 90 minus alpha. Yeah, does it. Does it? 90 minus alpha, 90 minus, oh, I got that mixed up. So 90 minus alpha, 90 minus alpha, then this would be 2 alpha and you're done. Because if this is 2 alpha, then this is alpha. Yeah, that's it. Good way. Yeah. Alternate segment, here's an example here that you all can look at, and then that's it for theory, at least for the easy part of it. Okay, so any questions? I am a little bit tired, so I don't think we'll do the algebra today. We could do that tomorrow. Or which one do y'all want to do next?